Hello and welcome. Welcome to Good Vibes Sleep. I'm so glad you're here right now. Wherever you are, whether you're lying in bed with the lights already off, curled up on a couch wrapped in something warm, or just settling in after a long day, I want you to know that you've made a wonderful choice tonight. You've chosen to slow down. You've chosen to let the world quiet for a little while. And together we're going to spend the next couple of hours somewhere truly special. Tonight we're going to the stars. Not in a rushed, information-packed kind of way. We're not going to race through facts or cram your mind full of dates and numbers. Tonight we're going to drift. We're going to wander gently through the night sky the way you might wander through a peaceful garden. Pausing when something catches our attention, sitting with things that feel beautiful, letting the vastness of it all wash over us like a warm, quiet tide. I want you to take a breath right now. A slow one. In through the nose, hold it just for a moment, and let it go. Let your shoulders drop. Let your jaw unclench. Let your hands relax wherever they're resting. You don't need to do anything tonight. You don't need to remember anything. You don't need to respond or react or perform. You can simply receive. You can simply be here in the dark under the sky. The night sky has been humanity's oldest companion. For as long as people have existed, for hundreds of thousands of years, long before cities, long before writing, long before any of the complications of modern life, human beings have lain down at the end of a long day and looked up at those points of light. They have wondered. They have felt small and safe at the same time, the way you sometimes do when something is so much bigger than you that your own worries seem to dissolve in comparison. Every single culture in human history has looked at the same stars you can see tonight. The ancient Egyptians looked up and saw gods and animals and stories written in light. Polynesian navigators studied these same stars so carefully that they could cross thousands of miles of open ocean without any instruments at all. Just the stars, the waves, and a deep, practiced trust. Aboriginal Australians, whose astronomical tradition is at least 65,000 years old and may be the oldest on Earth, looked up and saw not just the bright stars but the dark spaces between them, finding shapes in the dark bands of the Milky Way that they called the dark constellation. Shepherds in ancient Mesopotamia lay in the fields at night and named the patterns above them. And some of those names, Orion, Taurus, Scorpius, are the same names we still use today 5,000 years later. The stars connect us. Not just to each other across all of human history but to something much larger. To the universe itself. And tonight we're going to explore that connection. Slowly. Gently. Restfully. We'll start with our own star, the sun, and drift outward from there. We'll visit some of the most beautiful and beloved stars in the sky, wander through the ancient stories of the constellations, travel to the farthest reaches of the Milky Way, and arrive eventually at the deep, deep quiet of the universe's earliest moments. Along the way I'll share facts that I hope feel less like facts and more like gifts, small bright things to carry with you into sleep. So let's begin. Let's turn our attention upward and let the night sky tell us its stories. Let's begin where it makes the most sense to begin, with the star we know best. The one that warms our skin and grows our food and makes the sky blue and turns ordinary dust motes into tiny floating lanterns when it comes through the window at just the right angle in the afternoon. Let's begin with the sun. Now I know, the sun isn't a nighttime object. By the time most of you are listening to this, the sun has long since set. But I think that makes it an even more interesting place to start. Because the sun is still there, of course. It hasn't gone anywhere. It's just on the other side of the earth from you right now, faithfully illuminating the other half of the planet while your half rests in darkness. This is one of my favorite things to think about at night. The sun isn't absent, it's just around the corner. The sun has been shining for approximately 4.5 billion years. That number is almost too large to mean anything, but let's try to feel it for a moment rather than just think it. 4.5 billion years ago there was no Earth. There was no moon. There was no solar system as we know it. There was a vast, slowly rotating cloud of gas and dust drifting through space, the remnant of older, long-dead stars. And gradually, over millions of years, gravity began to pull that cloud inward. The center grew denser and hotter and denser still, until finally the pressure and temperature at the heart of it became so extreme that something extraordinary happened. Hydrogen atoms began to fuse together. They collided and merged and transformed, releasing energy in the process. A star was born. That star was our sun. And it has been doing exactly the same thing steadily and reliably ever since. Every single day for 4.6 billion years the sun has risen. Every single day, it has warmed whatever was below it. When the first tiny life appeared in Earth's ancient oceans, microscopic, simple, barely more than chemistry, the sun was already there. When the first fish crawled onto land, the sun was there. When dinosaurs walked through prehistoric forests and looked up at the sky, the same sun looked back down at them. When your great-great-grandparents were born, the sun was there. And tonight, on the other side of the planet from you right now, it is lighting someone's morning. There is something so deeply comforting about that continuity. The sun is the most reliable thing in the history of our planet. It has never called in sick. It has never taken a day off. It simply shines steadily and patiently and generously because that is what it is. It is a star, and shining is what stars do. The sun is, in every technical sense, an ordinary star. Astronomers classify it as a G-type main sequence star, what they sometimes call a yellow dwarf, although it's actually much closer to white than yellow. It sits squarely in the middle of the range of stellar sizes and temperatures. It is not the biggest star in the galaxy, not by a tremendous margin. It is not the brightest, not the hottest, not the most dramatic. In the vast community of stars, our sun is comfortably average. And yet, from our perspective, it is everything. It contains 99.86% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, every grain of interplanetary dust, all of it together adds up to just 0.14% of the total. The sun is not just the center of our solar system in the sense of being in the middle. It is the solar system, gravitationally speaking. Everything else is just circling it. The sun's diameter is about 109 times that of Earth. If the sun were hollow, you could fit about 1.3 million Earths inside it. And yet, for a star, it is genuinely modest in size. There are stars we'll visit later tonight that make our sun look like a pebble. At the heart of the sun, the core, temperatures reach about 15 million degrees Celsius. At that extraordinary temperature and pressure, hydrogen atoms don't behave the way we're used to. They fuse. 4 hydrogen nuclei collide and merge to form one helium nucleus, and in the process, a tiny amount of mass is converted directly into energy. This is nuclear fusion, the process that powers every star in the universe. Every second, the sun converts about 620 million metric tons of hydrogen into helium. And in the process, about 4 million metric tons of matter, 4 million tons, are converted into pure energy every single second. That energy is what you feel on your face on a summer afternoon. That energy is what makes plants grow. That energy, ultimately, is what feeds every living thing on Earth. Here is something I find profoundly beautiful about sunlight. The energy produced at the sun's core doesn't travel to the surface quickly. It doesn't shoot straight out the way you might imagine. Instead, it makes an extraordinarily slow, wandering journey, absorbed and re-emitted by particles over and over again, gradually working its way outward through the dense layers of the sun. This process takes, on average, somewhere between 10,000 and 170,000 years. The light that warms your face on a summer day may have been created at the sun's core before the pyramids of Egypt were built. before modern humans arrived in Europe, before the last ice age began. Then, once it finally reaches the sun's surface, it crosses the remaining 93 million miles of space between us in just 8 minutes and 20 seconds. 8 minutes and 20 seconds. The moment you step outside in the morning and sunlight touches your skin, you are receiving energy that began its journey in the distant past and has only just now arrived at its destination. You. The surface of the sun, called the photosphere, is a constantly churning, roiling sea of hot plasma at about 5,500 degrees Celsius. If you could somehow look at it closely, which you must never do without protection, you would see it is not a smooth, steady disk but a constantly bubbling surface, covered in granules, convection cells each roughly the size of Texas, rising and falling as hot plasma wells up from below, cools slightly and sinks back down. The entire surface of the sun is in constant, gentle, beautiful motion. Above the photosphere is the chromosphere, a layer of thinner, hotter gas that is normally invisible but becomes briefly visible during total solar eclipses as a thin pink ring around the darkened sun. And above that is the corona, the sun's outer atmosphere, which extends millions of miles into space and is, mysteriously, far hotter than the surface below it. The corona reaches temperatures of 1 to 3 million degrees, compared to the surface's 5,500 degrees. Scientists are still working to fully understand why the corona is so much hotter than the surface beneath it. The sun still keeps some of its secrets. The sun also has a gentle pulse, a barely perceptible heartbeat. It oscillates, contracting and expanding slightly, in cycles lasting about 5 minutes. It also has longer cycles. The famous sunspot cycle, which runs about 11 years, during which the number of sunspots on the solar surface rises and falls in a predictable rhythm. Sunspots are areas of intense magnetic activity that appear slightly darker than their surroundings. During solar maximum, they cluster and multiply. During solar minimum, the surface is calm and clear. The sun spins on its axis just as the Earth does. But because it's made of plasma rather than solid rock, different parts of it spin at different speeds. The equator takes about 25 days to complete one rotation, while the poles take closer to 35 days. This differential rotation is part of what creates the sun's complex, tangled magnetic field, and that magnetic field is ultimately responsible for sunspots, solar flares, and the streams of charged particles called the solar wind that sweep outward through the solar system and are responsible for the breathtaking northern and southern lights. The sun will continue to shine much as it does today for approximately another 5 billion years. Eventually, as its hydrogen fuel depletes, it will change. It will expand, slowly swelling into what astronomers call a red giant, growing large enough to potentially engulf the inner planets. But that is so impossibly far in the future, 5 billion years, that it barely registers as something to think about. In practical terms, the sun will be here, unchanging and reliable for longer than any timescale that has any human meaning. So tonight, as you lie in the dark, know that the sun is resting beneath your horizon, ready to rise again tomorrow, as it has done every single day for 4.6 billion years. It will not fail. It will not forget. It will come back with the morning, gentle and warm and impossibly faithful. That is our star. The nature of stars, what they are and why they matter. Now let's pull back a little. Let's float away from our particular star and look at stars in general, at what they are, how they're born, how they live their long lives, and what happens when they die. Because stars are not just pretty lights in the sky. They are the engines of the universe. They are the factories that make everything. Let me start with a number that I want you to just sit with for a moment. There are more stars in the observable universe than there are grains of sand on every beach and desert on Earth combined. Take a moment with that. Think of a beach, any beach. Think of how many grains of sand make up just one handful. Now imagine every beach you've ever seen, every desert you've ever heard of. The Sahara, the Gobi, the Atacama, the vast sand seas of Arabia. Every grain of sand on every one of those beaches and deserts, and there are still more stars. Estimates put the number of stars in the observable universe at somewhere around 200 sextillion. That's a 2 followed by 23 zeros. 200,000 million stars. And yet the night sky from Earth only shows us about 9,000 of them with the naked eye. The rest are simply too far away, too dim, hidden behind clouds of gas and dust or beyond the reach of our unaided vision. What we see on a clear night is just the tiniest, most local sample. The few thousand nearest neighbors in a community of almost unimaginable size. Stars are, at their most basic, enormous balls of hot gas held together by their own gravity and generating energy through nuclear fusion in their cores. That's the technical description. But I prefer to think of them as long-burning fires. Ancient, patient, self-sustaining fires that have been alight for millions or billions of years, floating in the dark between the galaxies, warming anything lucky enough to orbit close enough to benefit. A star begins its life inside what astronomers call a nebula, a vast cloud of gas and dust that drifts through space. These nebulae are among the most beautiful objects in the universe, and we'll visit some of them later tonight. They glow in colors that seem almost too vivid to be natural. Deep rose pinks, ethereal blues, warm ambers, soft violets. They are enormous beyond easy comprehension. Some nebulae are hundreds of light years across. And within them, gravity is always at work. Gravity is patient. It doesn't rush. But given enough time, it pulls things together. In the densest parts of a nebula, where a little more gas has gathered than elsewhere, perhaps because of a slight ripple from a distant supernova, gravity begins to concentrate matter. Over millions of years, a clump of gas grows denser and denser, pulling in more material from its surroundings. As it contracts, it heats up, the same way a bicycle pump gets warm when you compress the air inside it. The center of the forming star, called a protostar, grows hotter and hotter. And then, when the temperature at the core reaches about 10 million degrees Celsius, the critical moment arrives. Fusion begins. Hydrogen nuclei start colliding and merging. Energy is released. Light is born. The star switches on. It is one of my favorite things about the universe, that stars are not created by violence or force. They are created by patience and gravity, by the simple, quiet accumulation of matter over time, until suddenly the conditions are right and something extraordinary happens. A fire lights in the dark. Once a star reaches what astronomers call the main sequence, the long, stable phase of its life where it is steadily fusing hydrogen into helium, it enters a kind of equilibrium. The outward pressure of energy from fusion exactly balances the inward pull of gravity. The star neither collapses nor explodes. It simply burns. Steadily. For millions, hundreds of millions, or even billions and trillions of years, depending on its size. Here is something counterintuitive about stars. Bigger is not always better when it comes to lifespan. The most massive stars, the great blue supergiants that burn 100,000 times brighter than our sun, live fast and die young. They burn through their fuel so quickly that they may last only a few million years before exhausting themselves in a spectacular explosion. Our sun, by contrast, with its comfortable middling size, will have a total lifespan of about 10 billion years. And the smallest stars, the cool dim red dwarfs that are by far the most common type in the galaxy, burn so slowly and so efficiently that they can live for trillions of years. Since the universe is only about 13.8 billion years old, no red dwarf star has ever died of old age. Every single one that has ever formed is still shining, somewhere. Red dwarf stars deserve a special moment of appreciation, because they don't get enough attention. They are small, often just a tenth or a fifth the mass of our sun. They are cool, their surfaces glow deep red like embers rather than flames. They are dim, even the nearest one would be invisible to the naked eye. But they are enduring. They are eternal by any human measure. A red dwarf star will be still burning, still warming any planets that orbit it, long after our sun has faded and cooled and become a silent white dwarf. They are the tortoises of the stellar world, and they will outlast everything. The color of a star, by the way, tells you a great deal about it. Stellar color is directly tied to temperature. The coolest stars are red, deep crimson, like the embers of a dying fire. As stars get hotter, they progress through orange, then yellow, then white, and finally blue. Blue stars are the hottest and most massive. When you look up at the night sky and see the warm red of Betelgeuse in Orion's shoulder, or the cool blue-white of Rigel at his knee, you are reading the temperature of those stars directly with your eyes. The night sky is a color-coded temperature map, and once you know the code, you can never look at it quite the same way again. Stars also move. Not in ways you'd notice from night to night. The apparent motion of stars across the sky is caused by Earth's rotation and orbit, not by the stars themselves moving. But over thousands of years, the stars do drift, each following its own path through the galaxy. The constellation shapes we know today are different from the constellations ancient humans saw, and different again from what our descendants will see in 50,000 years. The star patterns are temporary, beautiful and meaningful now, but slowly shifting over deep time. There is something both melancholy and liberating about that thought. And then there is what happens when a star dies. The death of a star is not darkness. It is transformation. Depending on the star's mass, it can die in several different ways, and most of them are breathtaking. A star like our Sun, after expanding into a red giant and shedding its outer layers in a slow, beautiful exhalation, will leave behind a glowing shell of gas called a planetary nebula, misleadingly named because it has nothing to do with planets. The Helix Nebula, the Ring Nebula, the Cat's Eye Nebula, these are all planetary nebulae, the final exhaled breaths of sun-like stars. They glow for tens of thousands of years in extraordinary colors before gradually fading. At the center of each one is a tiny, dense, hot remnant called a white dwarf, the compressed core of the former star, now slowly cooling over billions of years. White dwarfs are about the size of the Earth but contain roughly the mass of the Sun. They are extraordinarily dense. And they are stable. They don't explode or fade quickly. They simply cool over billions upon billions of years, dimming from white to yellow to orange to red to brown to black. A slow, patient dimming in the dark. More massive stars end more dramatically. When a star several times the mass of our Sun exhausts its fuel, the core collapses catastrophically and the outer layers rebound in an explosion of almost incomprehensible violence called a supernova. For a brief time, days or weeks, a supernova can outshine an entire galaxy. The light from a single exploding star can be visible from billions of light years away. And in that explosion, the star scatters all of the elements it has spent its life creating: carbon, oxygen, nitrogen, iron, calcium, all of the building blocks of chemistry and life, out into space, where they mix with gas clouds and eventually find their way into new stars, new planets, new living things. The iron in your blood was forged in the heart of a dying star. The calcium in your bones. The oxygen in your lungs. The carbon that makes up your DNA. All of it was synthesized inside stars that lived and died before our solar system existed, and scattered into space, and eventually gathered into the cloud that became our Sun and our Earth and you. You are, in the most literally true sense imaginable, made of stardust. The universe made you out of itself. You are not separate from the cosmos. You are a part of it, assembled from its oldest, most fundamental materials. I find that thought one of the most comforting in the world. On the difficult nights, the nights when you feel small or lost or uncertain, remember that you are part of this. That the same matter that makes up the brightest stars in the night sky also makes up you. That the universe has been building toward you, one stellar generation at a time, for nearly 14 billion years. You belong here. You are made of this. the closest stars, our nearest neighbors. Let's take a journey now. A slow, drifting journey away from our sun, out through the local neighborhood of stars that surrounds us. Think of it like stepping out of your house on a quiet evening and walking slowly down your street, noticing the other lights in the windows, thinking about the lives being lived behind them. Our nearest stellar neighbor is Proxima Centauri, and it sits about 4.2 light-years from Earth. A light-year is the distance light travels in 1 year, moving at 186,000 miles per second, about 5.9 trillion miles. So Proxima Centauri is roughly 25 trillion miles away. If you drove there in a car at highway speed without stopping, the journey would take about 50 million years. It is, by any human measure, an incomprehensible distance. And yet in the context of the galaxy, it is our next-door neighbor. Proxima Centauri is a red dwarf, cool, dim, small, and ancient. It is gravitationally bound to a pair of brighter stars called Alpha Centauri A and Alpha Centauri B, and together the three form what is known as the Alpha Centauri system. On a clear night from the southern hemisphere, Alpha Centauri appears as one of the brightest stars in the sky, a brilliant yellowish point of light near the Southern Cross. It doesn't look like 3 stars from Earth, it looks like one. But that single point of light contains a whole solar system of complexity. In 2016, astronomers discovered a planet orbiting Proxima Centauri, a rocky, roughly Earth-sized world they named Proxima b, orbiting in the star's habitable zone. We don't know if it has an atmosphere. We don't know if it has water. We don't know if anything lives there. But the fact that our very nearest stellar neighbor may have an Earth-like planet in the right place for liquid water, it makes the universe feel more generous somehow, more hospitable. As if worlds like ours might not be rare exceptions but common features of the galaxy. A little further out, at about 8.6 light-years, we come to a star you know well, even if you've never thought of it as a neighbor: Sirius. The brightest star in the entire night sky. Sirius blazes in the winter sky for those in the northern hemisphere. A brilliant blue-white gem low in the south, so bright it almost seems too bright to be a star. It shimmers and flashes with color when near the horizon, its light split into a rainbow by Earth's atmosphere, giving it an almost festive appearance. Sirius is actually a binary system. Sirius A, the bright star you see, and Sirius B, a tiny white dwarf that orbits it every 50 years or so. Sirius B is completely invisible to the naked eye, you'd need a telescope to find it, but it is fascinating in its own right. Once, billions of years ago, Sirius B was the larger of the 2 stars in the system, burning hot and bright while Sirius A was still relatively young. It aged faster, exhausted its fuel, and collapsed into the dense white dwarf it is today. Now it's a hot, dense cinder orbiting its still active companion, the elder of the pair, now quiet, while the younger one burns on. The ancient Egyptians had a special relationship with Sirius. They called it Sopdet, and they worshipped it as a goddess associated with fertility and the flooding of the Nile. Every year, just before the annual Nile flood that was essential to Egyptian agriculture, Sirius would reappear in the pre-dawn sky after being hidden by the sun for several months. Its return was celebrated as a new year, a time of renewal and abundance. The Egyptian calendar was, in some sense, timed by the rhythm of a star. A star 8.6 light-years away was the clock that kept Egyptian civilization running. Beyond Sirius, at about 11.4 light-years, is Epsilon Eridani, a young, sun-like star surrounded by a disk of debris, possibly with planets in formation. At 11.9 light-years is Tau Ceti, another star remarkably similar to our Sun in size and temperature, and one that has long captured the imagination of astronomers searching for other Earth-like worlds. Tau Ceti has at least 4 candidate planets, one of which might possibly be within the habitable zone. These 2 stars, Epsilon Eridani and Tau Ceti, were the first targets of Project Ozma in 1960, the first organized search for radio signals from extraterrestrial intelligence. Scientists pointed their radio telescopes at these two friendly, sun-like neighbors and listened. They heard nothing definitive. But the act of listening, of pointing our ears at the stars and wondering, was itself a beautiful thing. These nearest stars give me a sense of the neighborhood we live in. Our little corner of the Milky Way is not empty or barren. Within just 15 light-years of Earth, there are about 50 known star systems, many of them containing multiple stars, and several with confirmed or candidate planets. We live in a reasonably well-populated neighborhood. The nearest stars are like lights in nearby windows, each one a different household with its own story, its own history, its own possible worlds. Orion, the great hunter. Let's drift now from our local neighborhood and move into the realm of the constellations, those magnificent patterns that humans have traced across the sky for thousands of years. And let's start with the most universally recognized constellation in the sky, Orion. There is something remarkable about Orion. It is visible from virtually every inhabited place on Earth. Whether you are in Iceland or Argentina, in Nigeria or Japan, in the middle of a city or on a remote mountainside, if the sky is clear and it is the right time of year, you can look up and find Orion. He is one of the few things truly shared by all of humanity, a common image in our collective sky. When you recognize Orion on a winter night, you are having exactly the same experience as every person who has ever looked up at the winter sky for the past 40,000 years. And Orion is not just recognized, he is magnificent. The constellation is dominated by 7 main stars. The reddish Betelgeuse at his right shoulder, upper left as you see him in the sky, the brilliant blue-white Rigel at his left knee, lower right, and the 3 perfectly aligned stars of his belt, Alnitak, Alnilam, and Mintaka, stretching diagonally across the center of the figure like the most elegant decoration imaginable. Below the belt, a short line of 3 dimmer stars marks his sword, and within that sword lies the Orion Nebula, one of the most spectacular objects in the entire night sky. Let's spend a moment with Betelgeuse because Betelgeuse is extraordinary. Betelgeuse is a red supergiant, one of the largest stars visible to the naked eye, and one of the largest stars known in the galaxy. If you placed Betelgeuse at the center of our solar system, where our Sun sits, its surface would extend somewhere past the orbit of Jupiter. It would swallow Mercury, Venus, Earth, Mars, and possibly Jupiter entirely. The space where we live would be inside the star. It is almost impossible to feel the scale of this with words alone. Our Sun, which we've established is 109 times the diameter of Earth, that Sun would be a tiny speck inside Betelgeuse. A small marble inside a house. When astronomers say Betelgeuse is a large star, they mean it in the most extreme possible sense of the word. Betelgeuse is also old. Or rather, it is approaching the end of its life. Massive stars burn through their fuel quickly, and Betelgeuse has been burning for about 8 to 10 million years, a blink compared to our Sun's total lifespan, but that's because it burns so fast and so furiously. At some point, no one knows exactly when, but astronomers estimate anywhere from now to within the next 100,000 years, Betelgeuse will explode in a supernova. When it does, it will be spectacular. It may briefly become bright enough to cast shadows at night. It may be visible in broad daylight. The sky over Earth will have, for a few weeks, a second brilliant point of light. And then it will fade, leaving behind a glowing nebula and possibly a neutron star at its core. In late 2019 and early 2020, Betelgeuse underwent what astronomers called the Great Dimming. Its brightness dropped significantly, more than it ever had in recorded observation. The astronomical world buzzed with excitement. Could this be the beginning of the end? Was Betelgeuse about to go supernova? As it turned out, the dimming was caused by a massive ejection of material from the star's surface, which cooled and formed a temporary dust cloud that blocked some of its light. Betelgeuse recovered. It is still there tonight, glowing warmly in Orion's shoulder, still waiting for its eventual spectacular end. Rigel, at Orion's foot, is equally impressive in a different way. Where Betelgeuse is red and enormous, Rigel is blue-white and blindingly luminous. Rigel burns about 120,000 times brighter than our Sun. If you replaced our Sun with Rigel, Earth would be uninhabitable. It would be roasted by the sheer intensity of Rigel's output. But at the distance Rigel actually sits, about 860 light-years away, it appears as simply the brightest star in Orion, a cool blue-white jewel at the hunter's foot. Now let's talk about Orion's belt, because the three belt stars deserve their own appreciation. Alnitak, Alnilam, and Mintaka are three hot, brilliant blue-white stars that happen to lie almost perfectly aligned as seen from Earth. They are not actually the same distance from us. Mintaka is about 900 light-years away, Alnilam about 1,340, and Alnitak about 800, but from our vantage point they form one of the most perfect, unmistakable lines in the sky. Three blue-white lights, equally spaced, running from lower right to upper left in a diagonal that draws the eye immediately. These three stars have been important to navigators for thousands of years, and not just as a beautiful pattern. Orion's belt rises due east and sets due west, no matter where you are on Earth. Not approximately east and west, exactly. If you're lost and need to find your cardinal directions, you can watch where the belt stars rise or set, and you have your compass. Nature built a navigation tool into the sky, and placed it in the most recognizable constellation, as if making sure humans would find it. The ancient Egyptians used Orion's belt to orient their most important monuments. The three Great Pyramids of Giza, those enormous, enduring structures that have stood for 4,500 years and are still among the most visited places on Earth, are arranged to mirror the three stars of Orion's belt, both in their spacing and in their slight offset from a straight line. Whether this was a deliberate alignment with the stars or a coincidence is debated by scholars, but the resemblance is striking. Those ancient builders looked up at the winter sky, saw the three stars of Orion's belt, and perhaps saw something worthy of being echoed in stone. And then there's the sword. Hanging below Orion's belt, three dimmer stars mark his sword. The middle star of the sword is actually not a single star at all. It is the Orion Nebula, also catalogued as Messier 42. With the naked eye, it appears as a slightly fuzzy, softly glowing spot. Through binoculars, it begins to show a faint, luminous cloud. Through a small telescope, it is breathtaking, a vast, swirling cloud of gas illuminated by the young hot stars embedded within it, glowing with soft greens and blues in the eyepiece, though photographs reveal its full rose-pink splendor in wavelengths our eyes can't detect. The Orion Nebula is a stellar nursery. Right now, as you lie there listening to this, new stars are being born in that cloud of gas. Over the last million years or so, hundreds of stars have formed from the nebula's material, and the process continues. The four brilliant young stars at the heart of the nebula, known as the trapezium, are among the youngest stars visible to amateur astronomers, just a few 100,000 years old, blazing with fierce blue-white light and illuminating the gas cloud around them. The Orion Nebula is not just beautiful. It is alive in the way that birth is alive, full of new beginnings, full of potential, full of the kind of energy that comes from things just getting started. The Orion Nebula is about 1,344 light-years away. The light you see when you look at it tonight left that nebula about 1,344 years ago, in the 7th century CE. The stars being born in it right now, you won't see for another 1,344 years. Orion is, in mythology, a great hunter. In Greek tradition he was the son of the sea god Poseidon, gifted with beauty and strength, who boasted he would kill all the animals of the earth. In different versions of the myth, he is placed among the stars by Zeus or by Artemis, the goddess of the hunt, who loved him. His faithful hunting dogs, the constellations Canis Major and Canis Minor, follow just behind him across the sky, and the bull he hunts, Taurus, faces him from the west. But other cultures saw entirely different stories in the same stars. The people of the Marshall Islands in the Pacific saw Orion's belt as three fishermen in a canoe. In some Native American traditions, the belt stars were three deer. In parts of ancient China, the belt and sword together formed a military official's insignia. In ancient Egypt, Orion was associated with Osiris, god of the underworld and rebirth. The stars of the belt mirrored in stone on the Giza Plateau, the hunter become a deity. Every culture that has looked at Orion has seen something different, brought something of their own world and their own understanding to those same bright stars. And every culture has looked. There are cave paintings in France, over 17,000 years old, that some researchers believe may depict Orion's belt. The constellation may be, quite literally, the oldest story humanity has ever told. The night's brightest lights, a tour of famous stars. Let's travel now through the night sky as if we were walking through a great gallery, stopping to admire the most brilliant lights, learning their names and their stories. Stars, like people, become more interesting when you know something about them. And the stars that are brightest in our sky are each, in their own way, remarkable. We've already visited Sirius, the brightest of all. Let's continue down the list. Canopus is the second brightest star in the night sky, and if you live in the northern hemisphere you may never have seen it. It is so far south that it never rises above the horizon for observers north of about 37 degrees latitude. For those in the southern hemisphere, however, Canopus is a familiar and beloved companion, a brilliant white star low in the southern sky. It lies in the constellation Carina, the keel of the old ship constellation Argo. What makes Canopus particularly interesting to me is what it does today, right now in the 21st century. It helps spacecraft navigate. Because Canopus is extremely bright, easily identifiable, and located far from the ecliptic plane where most solar system objects orbit, it serves as a reliable fixed reference point for the navigation systems of satellites and deep space probes. The Voyager spacecraft used Canopus as a navigation star. NASA's Mars rovers have used Canopus. When we need to know which way a spacecraft is pointing in the vast dark of space, we often look to Canopus. A star so ancient and so steady that modern robots use it to find their way. Arcturus is the third brightest star in the night sky and the brightest star in the northern celestial hemisphere. It dominates the spring and early summer sky for northern observers, a warm orange-yellow point of light high in the south on spring evenings. Arcturus is a giant star, about 25 times the diameter of our Sun, in the late stages of its life, having already exhausted the hydrogen in its core and expanded outward. It glows with a distinctive warmth that distinguishes it from the blue-white of younger, hotter stars. Arcturus has a story that connects it to the first great World's Fair of the 20th century. When the Century of Progress World's Fair opened in Chicago in 1933, the ceremony was triggered by the light of Arcturus. Astronomers aimed telescopes at the star, and the light they collected was used to generate an electrical signal that switched on the lights of the fairground. Why Arcturus? Because it was calculated that light leaving Arcturus at the time of the previous Chicago World's Fair in 1893 would be arriving at Earth just in time for the 1933 opening. The fair was literally opened by 40-year-old starlight, a piece of poetry written in physics and timing. Vega, the fifth brightest star in the night sky, holds a special place in the calendar of the northern sky. In high summer, it passes almost directly overhead for observers in the middle latitudes of the northern hemisphere, blazing blue-white at the zenith like a frozen firework. It is the brightest star in the small constellation Lyra, the Lyre, and it forms one corner of the summer triangle along with Deneb in Cygnus and Altair in Aquila. Vega has been our pole star before. Because Earth's axis wobbles slowly, a process called precession, which traces a great circle in the sky over 26,000 years, the North Celestial Pole moves through a succession of different stars over the millennia. Currently, Polaris sits near the pole. But about 12,000 years ago, Vega was our pole star, the star ancient peoples of the Northern Hemisphere could look to as the one fixed point in the sky. And in about 12,000 years, Vega will hold that position again. It has a turn every 26,000 years, patiently waiting its rotation in the pole position. Vega is also famous in popular culture as the destination of the radio signal received in Carl Sagan's novel and film Contact, the nearest prominent blue-white star, a natural target for imaginative first contact stories. It is 25 light-years away, close enough to feel like a neighbor, bright enough to dominate its part of the sky. Capella, the sixth brightest star in the sky, is one of the most interesting systems to understand, because it is not, in fact, one star. Capella is a system of 4 stars, 2 bright yellow giants orbiting each other every 104 days, and a distant pair of dim red dwarfs also gravitationally bound to the system. The 2 central yellow giants are each roughly the size of what our Sun will eventually become in its old age, expanded, somewhat cooler, glowing with a warm golden light. They orbit so close together that no telescope can separate them visually, only spectroscopy reveals the system's true nature. Capella is the brightest star in the constellation Auriga, the charioteer, and it holds a special place in the winter sky of the Northern Hemisphere, reaching its highest point in the sky during the long nights of December and January, when it transits nearly overhead. It is one of the most northerly of the first magnitude stars, visible from every inhabited location in the Northern Hemisphere. On the coldest, clearest winter nights, Capella blazes steadily overhead with that distinctive warm golden tone, one of the most reassuring lights in the winter sky. Aldebaran, the angry red eye of Taurus the bull, is the kind of star that looks exactly like what it is. It glows with a deep orange red that is immediately obvious to the naked eye, warmer and redder than most other bright stars, a smoldering ember-like color that gives Taurus its fierce expression. Aldebaran is a red giant, about 44 times the diameter of our Sun, and it sits just 65 light-years away, close by stellar standards. The name Aldebaran comes from Arabic, al-Dabran meaning the follower, because it appears to follow the Pleiades star cluster across the sky. The Pleiades rise first in the evening sky, and Aldebaran rises after, following dutifully behind. This relationship between Aldebaran and the Pleiades has been noted by astronomers and storytellers across many cultures, each one reading a different relationship between the follower and the ones it follows. Spica is the brightest star in the constellation Virgo, and it played a significant role in one of the most important discoveries in the history of astronomy. Around 127 BCE, the Greek astronomer Hipparchus compared the position of Spica to measurements made 150 years earlier, and found that it had shifted slightly, not because the star had moved, but because Earth's axis had wobbled, slowly shifting the reference frame of the sky. This was the discovery of the precession of the equinoxes, the 26,000-year wobble we mentioned when talking about Vega and Polaris. Spica, a distant point of blue-white light 250 light-years away, helped a Greek astronomer discover something fundamental about the motion of our own planet. These are the kinds of connections I love. The way understanding the sky teaches us things about ourselves, about the Earth, about our own position in the cosmos. The stars are not just beautiful objects to look at. They are clocks and compasses and mirrors, reflecting truths about who we are and where we live. The North Star and the art of finding your way. Let's talk about Polaris, the North Star, because it deserves its own section. Of all the stars that humans have relied upon over the centuries, Polaris holds perhaps the most important practical place. It has been, quite literally, a guiding light for explorers, navigators, and travelers for thousands of years. Polaris sits at the end of the handle of the Little Dipper, which is part of the constellation Ursa Minor, the Little Bear. On most nights, it's not the most visually impressive star in the sky, it's only moderately bright, outshone by many others. But what makes Polaris special is not its brightness. It is its position. Due to a happy accident of cosmic alignment, Polaris sits almost exactly above Earth's geographic North Pole. The Earth's axis, the imaginary line running through the planet from pole to pole, around which the whole Earth rotates, points almost directly at Polaris. This means that as the Earth spins, all the other stars appear to rotate around Polaris in great circles. Every star in the northern sky traces a circle around this one fixed point. Polaris alone doesn't move, or rather, it moves only a tiny amount, close enough to the pole that the difference is negligible. It is the one still point in the turning sky. This makes it extraordinarily useful. If you can find Polaris, you know which way is north. Exactly north. Not approximately, not with a margin of error, north. And if you know your latitude, how far from the equator you are, you can find that too by measuring how high above the horizon Polaris sits. At the North Pole, Polaris would be directly overhead, 90 degrees up. At the equator, it would be right on the horizon, 0 degrees. In London at about 51 degrees north latitude, it sits 51 degrees above the northern horizon. In New York at 40 degrees north, it sits 40 degrees up. The star is a built-in sextant. Sailors used this fact for centuries to navigate the open seas. By night, they would find Polaris, measure its height above the horizon, and know their latitude with reasonable precision. Combined with knowledge of the sun's position by day, they could determine their position on the globe far from any familiar coastline. The star was, in the most practical sense, a lifeline. But finding Polaris isn't always immediately obvious if you don't know where to look. The most common method, and one you can use anywhere in the northern hemisphere, is to first find the Big Dipper, which is the most distinctive star pattern in the northern sky. The Big Dipper is part of the constellation Ursa Major, the Great Bear, and it looks exactly like what its name suggests. A large ladle or dipper with a bowl of 4 stars and a handle of 3. Once you find the Big Dipper, look at the 2 stars that form the outer edge of the bowl, the side farthest from the handle. These 2 stars are called Merak and Dubhe, and they are known as the pointer stars because if you draw a line from Merak through Dubhe and extend it about 5 times the distance between them, you will arrive at Polaris. It works every time. This simple technique, 2 stars pointing to the pole, was taught to children and sailors and explorers for generations. It is still useful today. On any clear night in the northern hemisphere, you can take your bearings by the stars, the same way humans have done since before recorded history. Polaris itself, by the way, is not a single star. It is a triple star system, Polaris A, a bright yellow supergiant, Polaris UB, a smaller companion discovered in 2006 that orbits Polaris A every 30 years, and Polaris B, a more distant companion visible through a small telescope. 3 stars appearing as one steady light, holding their position above the North Pole while the rest of the sky wheels around them. And here is something to hold in mind as you settle towards sleep. Polaris has not always been the North Star and will not always be. The wobble of Earth's axis, that 26,000-year precession cycle, means the pole traces a slow circle through the sky, and different stars take their turn as the celestial north marker. About 3000 BCE, when the Egyptian pyramids were being built, the pole star was a much dimmer star called Thuban in the constellation Draco. In about 12,000 years, as we mentioned, Vega will hold the position. In 26,000 years, Polaris will be the pole star again. The sky is not fixed. It changes on scales we can barely imagine. But on any given human lifetime, on the scale of your life and your parents' lives and their parents, Polaris holds steady. It will be there tomorrow night, exactly where it is tonight. Exactly where it was last year. Where it was when your grandparents were born, and when their grandparents were born. A constant in the changing world. A fixed point above the turning Earth. The Milky Way, our cosmic home. Now let's zoom out. Let's leave the neighborhood of our local stars and drift upward. Imagine rising above the solar system, above the local cloud of nearby stars, rising higher and higher until the individual points of light blur together into a grand structure. Let's look at the Milky Way. The Milky Way is our galaxy, the vast, spinning collection of stars, gas, dust, and dark matter within which our solar system makes its home. It is, in the most literal sense, our cosmic home. Not just Earth, not just the solar system, but the entire neighborhood of billions of stars that constitutes the structure we belong to. The Milky Way is a barred spiral galaxy. If you could see it from above, truly from outside looking down, it would look something like a hurricane as seen from a satellite. A bright, dense core surrounded by sweeping spiral arms made of stars and gas and dust, all slowly rotating. But unlike a hurricane, the arms are not tightly wound. They extend gracefully outward, following long sweeping curves that take millions of years to trace. And cutting across the center, connecting the inner parts of the arms, is a bar. A roughly linear distribution of stars that gives the galaxy a slightly elongated appearance at its core. Our solar system sits in one of the spiral arms, a minor arm called the Orion arm, or sometimes the local arm, about 26,000 light-years from the galactic center. We are not in the center, not at the edge, but somewhere in the middle distance, about halfway out from the core to the galaxy's rim. In the great city of the Milky Way, we live in the suburbs. The Milky Way is about 100,000 light-years across. It contains somewhere between 100 and 400 billion stars. The uncertainty is large because much of the galaxy is hidden from us behind clouds of dust, and because counting stars in a galaxy is, obviously, an extraordinarily difficult task. 200 billion is a reasonable middle estimate. 200 billion individual suns, each one potentially with its own system of planets, each one perhaps warming worlds of its own. There is real comfort in that. When you look up on a clear, moonless night far from city lights, you can see the Milky Way with the naked eye as a faint, irregular band of soft light stretching across the sky. This is not a separate object in the sky, you are inside it. What you're seeing when you look at the Milky Way band is the view from within the disk of the galaxy, looking along the plane of it. The band appears because in that direction, there are far more stars than in any other direction. You're looking through the galaxy's depth rather than across it. In the direction of the constellation Sagittarius, the band is brightest and most complex, because that is the direction of the galactic center, where the density of stars is highest. The galactic center is, in many ways, the heart of the Milky Way, dense, complex, ancient, and extraordinary. At its core sits Sagittarius A*, a supermassive black hole with a mass about 4 million times that of our Sun. Sagittarius A** is not actively feeding at the moment. It is relatively quiet compared to the active galactic nuclei seen in other galaxies. But it has had episodes of activity in the past, and occasional small bursts still occur when material falls into it. 4 million solar masses in a region of space barely larger than our solar system. The physics at the galactic center are extreme by any measure. Stars orbit Sagittarius A** at extraordinary speeds. One star, called S2, has been tracked for over 20 years and completes a full orbit around the black hole in just 16 years, traveling at speeds up to 3% of the speed of light. By watching S2 and other stars orbit around an invisible point, astronomers were able to prove beyond any doubt that a supermassive black hole resides at the center of our galaxy. Our solar system orbits the galactic center too, of course. It takes us about 225 to 250 million years to complete one full orbit, a period sometimes called a galactic year or cosmic year. In the time since our solar system formed, we have completed between 18 and 20 orbits of the galaxy. Since life first appeared on Earth, we have gone around the galactic center about 20 times. Since the dinosaurs went extinct, we have traveled about a quarter of the way around. The Milky Way is not alone. It is the largest member of a small cluster of galaxies called the Local Group, which contains about 54 galaxies of various sizes. The Andromeda Galaxy, which we'll visit shortly, is the only other large spiral galaxy in the group. Most of the rest are small, irregular, or dwarf galaxies, many of them satellites orbiting either the Milky Way or Andromeda. The Milky Way itself has several satellite galaxies orbiting it. The most prominent are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere as two separate wisps of soft light near the Southern Cross. They were named after the Portuguese explorer Ferdinand Magellan, whose expedition noted them during the first circumnavigation of the Earth in the 1520s, though of course the peoples of the southern hemisphere had known and named them for millennia before that. The Magellanic Clouds are irregular galaxies. They don't have the orderly spiral structure of the Milky Way. The Large Magellanic Cloud is about 160,000 light-years away and contains about 30 billion stars. The Small Magellanic Cloud is about 200,000 light-years away and contains about 3 billion stars. There is something deeply moving to me about the idea of our galaxy having companion galaxies, smaller neighbors that orbit along with us through the cosmos. The universe arranged itself not just into isolated galaxies but into clusters and groups and families. Even galaxies are not alone. The Milky Way is ancient. The oldest stars in our galaxy are nearly as old as the universe itself. Some have been measured at about 13.6 billion years old, just 200 million years younger than the Big Bang. These ancient stars, found mostly in the globular clusters that surround the galaxy, were born in the earliest epoch of cosmic history, when the universe was young and hot and very different from what it is today. They have been burning steadily ever since, witnesses to the entire history of everything. On a dark, clear night, lie on your back and look up at the Milky Way. Watch it stretch from one horizon to the other, broader in the direction of Sagittarius, more scattered and complex toward Cygnus in the north. Let yourself feel what you are actually looking at, not just a pretty stripe of light but the galaxy itself, the structure you belong to. The neighborhood of 200 billion stars in which your own sun is one ordinary, unremarkable, irreplaceable member. You are inside the Milky Way. You have always been inside it. And when you look at that pale band of light, you are looking at your own home from the inside, which is, when you think about it, one of the most beautiful things imaginable. The constellations, stories in the sky. Let's slow down now. Let's wander through the sky more gently, the way you might browse through a gallery of paintings, letting each one hold your attention for a while. The constellations are humanity's oldest artwork, patterns of meaning traced across the sky with nothing but imagination and longing and the deep human need to make sense of the world. There are 88 officially recognized constellations, defined by the International Astronomical Union in 1930. They cover the entire sky without overlap. Every point of sky belongs to one constellation or another, the way every point of a country belongs to one state or province or county. No star is unaccounted for. Every star has a neighborhood. The constellation boundaries were formalized in 1930, but the patterns themselves are much, much older. Most of the constellations in the northern hemisphere trace back to ancient Mesopotamian and Greek astronomy, with many others added by European astronomers during the Age of Exploration when the southern hemisphere sky was first systematically catalogued. The zodiac constellations hold a special place, because they mark the path of the sun, moon, and planets across the sky over the course of the year. The zodiac is a belt of sky centered on the ecliptic, the apparent path the sun traces against the background stars as seen from Earth over the course of a year. Because all the major planets orbit the sun in roughly the same plane, they all appear within this belt as well. When astronomers say Jupiter is in Taurus, or Mars is in Scorpius, they mean those planets are currently in the region of sky occupied by those constellations. The 12 zodiacal constellations, Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpius, Sagittarius, Capricornus, Aquarius, Pisces, were established by Babylonian astronomers around 500 BCE, though their origins go back even further. The Babylonians divided the ecliptic into 12 equal segments to create a consistent system for tracking the movement of celestial objects, and they assigned a constellation to each segment. Some of the constellations they used are the same ones we use today. There is also a 13th constellation that the sun passes through, Ophiuchus, the serpent-bearer, but this was not included in the traditional zodiac. Ophiuchus sits between Scorpius and Sagittarius, and the sun spends more time in it than it does in Scorpius. But the Babylonian 12-month system didn't accommodate 13 constellations, and so Ophiuchus has been the overlooked constellation ever since, present but uncelebrated, sitting quietly at the edge of the zodiac. Let's visit some of the most beloved constellations one by one. Ursa Major, the Great Bear, is one of the largest and most recognized constellations in the northern sky. Within it lies the Big Dipper, not actually a separate constellation but an asterism, a pattern within a constellation, which is arguably the most recognized star pattern in the northern hemisphere. The Big Dipper's 7 stars form a shape so obvious and so easily memorable that it serves as the primary waypoint for navigating the northern sky. Find the Big Dipper and you can find almost anything else. The constellation of the Great Bear has been recognized by an extraordinary range of cultures across the northern hemisphere. Ancient Greeks saw a bear. Many Native American tribes saw a bear with 3 hunters following it. Ancient Egyptians saw a bull's thigh. Various indigenous peoples of North America saw different animals and figures. But the remarkable thing is that across many cultures separated by thousands of miles and thousands of years, the same group of stars was seen as the same basic shape. A large animal like a bear or bull or other quadruped in the same region of the sky. Somehow, these 7 stars suggested an animal to independent human observers across the world. The 2 stars at the end of the Big Dipper's handle, Alioth and Mizar, have their own interesting story. Mizar is a double star, 2 stars orbiting each other so close that a sharp-eyed observer can just separate them without a telescope. Just next to Mizar is an even fainter star called Alcor, which has historically been used as a test of eyesight. If you can see Alcor next to Mizar, your eyes are excellent. Alcor and Mizar were known as the horse and rider in some traditions. And as if the story weren't interesting enough, more recent observations have revealed that Mizar itself is actually a quadruple star, 2 pairs of binary stars, all orbiting each other. What looks like one modest point of light in the handle of the Big Dipper is actually 4 stars in a complex gravitational dance. Cassiopeia, the Queen, is one of the most distinctive constellations in the northern sky, and one of the most convenient. Cassiopeia is circumpolar for observers in mid and high northern latitudes, meaning it never sets below the horizon. While most stars rise and set as the Earth rotates, Circumpolar stars make a complete circle around the pole, visible at any hour of any night throughout the year. Cassiopeia traces a distinctive W or M shape, depending on its orientation in the sky at any given time, making it immediately recognizable. It sits on the opposite side of Polaris from the Big Dipper like a counterbalance. When the Big Dipper is high in the sky, Cassiopeia is low and vice versa. In mythology, Cassiopeia was a queen of ancient Ethiopia who was punished for her vanity by being chained to her throne and set spinning in the sky, sometimes right side up and sometimes upside down. A fate that conveniently explains why her constellation appears in different orientations throughout the night and year. Her husband King Cepheus sits beside her in the sky, a fainter and less distinctive constellation, and their daughter Andromeda and her hero Perseus are arranged nearby, as if the family has been placed in the sky to spend eternity together. In 1572, a supernova appeared in Cassiopeia, suddenly and dramatically bright, visible in broad daylight for several weeks. The Danish astronomer Tycho Brahe observed it carefully and wrote a book about it called De Nova Stella, concerning the new star, giving us the word nova, and by extension supernova, that we still use today. What Tycho saw was the death of a star, a white dwarf in a binary system that had accumulated too much mass and exploded. The remnant of that explosion, called Tycho's supernova remnant, is still expanding today, a glowing shell of gas that tells the continuing story of a star that briefly shone brighter than Venus and then vanished in a matter of months. Perseus, the hero, lies between Cassiopeia and Taurus in the sky, and it contains one of the most interesting variable stars known, Algol. The name comes from the Arabic al-Ghul, meaning the demon or the ghoul, and it was associated with the head of Medusa that Perseus holds in his hand. Algol is a fascinating object because it dims noticeably every 2.87 days. A change in brightness that is visible to the naked eye if you know what you're looking for. This is caused by the fact that Algol is a binary system where one star periodically passes in front of the other from our perspective, temporarily blocking some of its light. These eclipsing binaries are common, but Algol was the first one studied in detail, and it has fascinated astronomers for centuries. Its regular dimming was explained by John Goodricke in 1783, who was remarkably both deaf and 18 years old at the time, and who died just 2 years later before seeing his discovery become fully accepted. Perseus also hosts the double cluster, two open star clusters called H and Chi Persei, visible to the naked eye as a fuzzy double patch of light and breathtaking through binoculars. Each cluster contains hundreds of young, hot, blue stars, born from the same large molecular cloud some 13 million years ago. They sit about 7,500 light-years away and are among the most spectacular objects in the night sky for binocular observers. Let's visit the Summer Triangle, that great asterism formed by 3 bright stars in 3 different constellations: Vega in Lyra, Deneb in Cygnus, and Altair in Aquila. For Northern Hemisphere observers, the Summer Triangle dominates the evening sky from late spring through autumn, rising in the northeast at dusk and reaching high overhead by midnight in summer. Deneb, marking the tail of Cygnus the Swan, is one of the most interesting stars in the sky for a reason that isn't immediately obvious: its extreme distance. Deneb is genuinely far away. Estimates range from about 1,400 to 2,600 light-years, with the true distance still somewhat uncertain. What makes this remarkable is that despite being so distant, Deneb is still one of the brightest stars in the sky. To appear so bright from so far away, Deneb must be intrinsically luminous to an extraordinary degree. Estimates suggest it may be 100,000 to 200,000 times more luminous than our Sun, making it one of the most intrinsically brilliant stars known. If Deneb were as close to us as Sirius, it would appear as a crescent moon in the sky, casting visible shadows at night. Altair, the eagle's bright eye in Aquila, is a near neighbor at just 17 light-years away, and it has an unusual property. It spins very fast. Altair rotates on its axis in less than 10 hours, compared to our Sun's 25 days, and this rapid rotation gives it a distinctly flattened shape, bulging noticeably at the equator. The star is about 20% wider at its equator than at its poles, a squashed ball spinning at tremendous speed. In 2006, astronomers produced the first images of Altair that resolved its disk, confirming the flattening. A star that we can not just observe as a point but actually see as a shape. That's remarkable. Lyra the Lyre, the tiny constellation containing Vega, also hosts one of the most famous objects in the deep sky, the Ring Nebula. The Ring Nebula is a planetary nebula, the glowing shell of gas expelled by a dying sun-like star. It looks, through a telescope, exactly as it sounds. A ring, a circle of glowing gas hanging in the sky like a cosmic smoke ring. At its center is the white dwarf remnant of the star that once blazed there. The Ring Nebula is about 2,300 light-years away and about 1 light-year across. It has been gently expanding since the star shed its outer layers about 6,000 years ago. Nebulae, the nurseries and gardens of the stars. Let us drift now to some of the most beautiful places in the universe. Nebulae, those vast clouds of gas and dust that glow with an almost unreal luminosity in astronomical photographs, are the nurseries where stars are born and the gardens where dying stars leave their final gifts. The word nebula comes from the Latin for mist or cloud, and it is a good description. These are not solid objects. They are, in a sense, almost nothing, gas so thin that the best vacuum chambers on Earth would be considered dense by comparison. And yet, spread across light-years of space, even this almost nothing glows. The glowing comes from two sources. Some nebulae glow by their own light, excited by the energy of nearby hot stars, while others glow by reflected light, like cosmic mirrors. The Orion Nebula, which we visited earlier, is an emission nebula. It glows by its own light. The hot young stars of the trapezium at its heart emit powerful ultraviolet radiation that ionizes the surrounding gas, causing it to glow in the same way a neon sign glows. Electrons knocked into excited states and then falling back, releasing photons of light. Different elements emit different colors. Hydrogen glows deep red and pink, oxygen glows blue-green, sulfur glows red-orange. The Orion Nebula is currently undergoing enormous star formation. Within the last million years, hundreds of new stars have formed from its material, and the process continues. It is one of the closest active star-forming regions to Earth, just over 1,300 light-years away. The Eagle Nebula, about 7,000 light-years away in the constellation Serpens, contains the Pillars of Creation, perhaps the most famous astronomical image in history. The photograph taken by the Hubble Space Telescope in 1995 showed 3 towering columns of gas and dust rising against a backdrop of glowing nebula, their surfaces sculpted by the fierce radiation and stellar winds of nearby young stars. The tallest pillar is about 4 light-years tall, more than the distance from our Sun to its nearest neighbor. Within these pillars, new stars are forming right now, hidden from view by the dense gas and dust, gathering matter around them, building toward the moment when they will switch on and their light will finally escape into the universe. Interestingly, astronomers believe the pillars of creation may no longer exist in their current form. The light we see from them left about 7,000 years ago. Analysis of the infrared light from the region suggests that a nearby supernova explosion may have already destroyed the pillars, but the light from that destruction won't reach us for another 1,000 years or so. We are looking at the past as always and seeing something that may already be gone. The Crab Nebula in the constellation Taurus, is the remnant of a supernova that was witnessed by Chinese and Arab astronomers in 1054 CE. They recorded that a new star appeared in the sky, so bright it was visible in daytime for 23 days, and visible at night for almost 2 years before fading. Today, nearly 1,000 years later, the gas blown out by that explosion is still expanding, forming a complex, tattered cloud about 11 light-years across, laced with glowing filaments of gas. At its center is a pulsar, a rapidly spinning neutron star, the compressed core of the original star that exploded. The Crab pulsar rotates 30 times per second, emitting beams of radio waves and X-rays with clockwork precision. An entire star compressed to the size of a city, spinning 30 times a second. The Crab Nebula is one of the most studied objects in the sky, partly because it is young enough that we know exactly when it was created and can track how it has changed. The Helix Nebula in Aquarius is one of the largest planetary nebulae in apparent size, and one of the closest to Earth at about 700 light-years. In photographs, it looks strikingly like a giant eye, a circular ring of glowing gas with a blue-green center, surrounded by an outer halo. This visual resemblance to a human eye earned it the nickname, the Eye of God, in popular culture. It is about 2.5 light-years across. If Proxima Centauri, our nearest neighbor, were at the center, the outer edge of the nebula would reach nearly to our own solar system. The white dwarf at its center has been cooling for about 10,000 years, slowly dimming in the heart of the beautiful cloud it created when it died. The Lagoon Nebula, visible to the naked eye in the constellation Sagittarius as a faint smudge near the edge of the Milky Way band, is a vast star-forming region about 4,100 light-years away. It glows with warm pinks and purples in photographs, and contains a cluster of young hot stars whose radiation sculpts the surrounding gas into dramatic shapes. The Lagoon Nebula is one of only 2 emission nebulae visible to the naked eye from the northern hemisphere, the other being the Orion Nebula. On the darkest nights, you can see both without any optical aid, just by knowing where to look. 2 stellar nurseries visible to the naked human eye, light-years across, thousands of light-years away, glowing with the light of new stars. The Rosette Nebula in Monoceros is a ring-shaped emission nebula about 5,200 light-years away. Its central region has been cleared of gas by the young stars at its center, creating a hollow appearance. The outer ring of gas and dust continues to glow with the familiar deep pinks of hydrogen emission. Embedded in the nebula are small, dense globules of gas and dust, potential future solar systems in early formation, dark shadows against the glowing background. These nebulae remind me of gardens, but gardens on a scale where the flowers are light-years across and grow for millions of years. A cosmic garden where the gardener is gravity and time and the physics of glowing gas. And like any garden, the nebulae contain both endings and beginnings. The material of dead stars nourishing new ones. Old light feeding new fires. Globular clusters, ancient cities of stars. Now let's talk about globular clusters, some of the most ancient and beautiful structures in the galaxy. A globular cluster is a roughly spherical collection of stars, tightly packed together by gravity, that orbits the center of a galaxy as a unit. Our Milky Way has somewhere between 150 and 200 known globular clusters, each one a compact ball of ancient stars, floating in the outer halo of the galaxy. Globular clusters are not like open clusters. The loose, young groups of stars like the Pleiades, scattered across hundreds of light-years and slowly drifting apart. Globular clusters are ancient, dense, and gravitationally stable. They have been together for billions of years. They will be together for billions more. The stars in globular clusters are, on average, some of the oldest in the universe. Many globular cluster stars formed 12 to 13 billion years ago, in the very early history of the cosmos. when the universe was young and the first generations of stars were lighting up the darkness. To look at a globular cluster is to look at the ancient past, at stars that have been burning since before our solar system existed, since before Earth, since before the Sun. Messier 13, the Great Globular Cluster in Hercules, is probably the most famous globular in the northern sky. It sits about 25,000 light-years away in the constellation Hercules, and contains roughly 300,000 stars packed into a sphere about 145 light-years across. To the naked eye, it's a faint, fuzzy spot, the kind of thing you might mistake for a dim comet. Through binoculars, it begins to show its globular nature. Through a telescope, it resolves into a dazzling ball of light, densest at the center and fading gradually toward the edges, like a three-dimensional cloud of fireflies frozen in a moment of perfect spherical symmetry. In 1974, the Arecibo radio telescope in Puerto Rico sent a famous message into space. A simple binary code encoding basic information about humanity, mathematics, and our location in the galaxy. The message was directed at Messier 13. The target was chosen because M13's 300,000 stars represent a reasonably large audience, and it was roughly in a convenient direction for Arecibo to aim at the time. Of course, M13 is 25,000 light-years away, so the message won't arrive for 25,000 years, and if anyone receives it and sends a reply, we won't hear back for another 25,000 years after that. A conversation that will take 50,000 years. But the act of sending it, of composing a message to 300,000 ancient suns, was itself meaningful. An expression of hope. A greeting sent across the dark. Omega Centauri, visible in the southern hemisphere, is the largest globular cluster in the Milky Way, and one of the most remarkable objects in the galaxy. It contains roughly 10 million stars and is about 17,000 light-years away. Omega Centauri is unusual in several ways. It is far larger than any other globular cluster. It contains multiple populations of stars of different ages, suggesting it may have experienced multiple episodes of star formation. And at its center, there may be an intermediate mass black hole, something between the stellar mass black holes formed by individual stars and the supermassive ones at galactic centers. Some astronomers believe Omega Centauri may actually be the core of a small galaxy that was absorbed by the Milky Way billions of years ago, its outer stars stripped away and its dense center surviving as what we now see as a globular cluster. 47 Tucani, another southern globular visible near the Small Magellanic Cloud, is almost as spectacular as Omega Centauri and arguably even more beautiful in photographs. A dense, glittering ball of golden-orange stars, densest at the center where it blazes like a compressed fire. It contains millions of stars and is about 15,000 light-years away. Near its center, astronomers have found dozens of millisecond pulsars, old neutron stars that have been spun up to extraordinary rotation speeds by accreting material from companion stars. These pulsars rotate hundreds of times per second, their radio beams sweeping the sky like the most precise clocks in the universe. The existence of globular clusters is one of the things I find most moving about the cosmos. These ancient structures, born 12 or 13 billion years ago when the universe was young, have survived intact through all of cosmic history. While stars formed and died, while galaxies collided and merged, while the universe expanded and cooled, these compact balls of ancient stars stayed together, bound by gravity, loyal to each other across billions of years. They have been drifting through the galaxy since before Earth existed. They will still be drifting when our sun is gone. They are the elders of the stellar world, ancient, dense, enduring. There is deep comfort in that kind of persistence. Andromeda and the neighboring galaxies. Let us travel even further now. Further than we've gone before. Let's leave the Milky Way entirely and visit our nearest galactic neighbor, the Andromeda Galaxy. On a clear, dark autumn night, in the constellation Andromeda, you can find with the naked eye a small, faint oval smudge of light. It is subtle, easily missed by a casual observer, but unmistakable once you've found it. That smudge of light is the Andromeda Galaxy, also known as Messier 31. And it is the most distant object that human eyes can see without optical aid. The light you see when you look at Andromeda left that galaxy 2.537 million years ago. Not 2.537 million miles away, 2.537 million light-years. The light has been traveling through space for 2.5 million years, and only now, tonight, is it completing its journey by entering your eye. 2.5 million years ago, our ancestors were early Homo habilis, just beginning to use stone tools on the African savanna. The Andromeda Galaxy sent light toward Earth at that moment, and it has been traveling ever since, and tonight it arrives. Every night you look at Andromeda, you are receiving a message that was sent before humanity existed in any meaningful sense. And yet, despite this almost incomprehensible distance, Andromeda is our nearest large galactic neighbor. In the cosmos, it is practically next door. The Andromeda Galaxy is a barred spiral galaxy much like our own Milky Way, though somewhat larger. It contains approximately 1 trillion stars, compared to our 200 to 400 billion. Its disk is tilted slightly toward us, which is why we see its elongated oval shape rather than a full face-on circle. Like the Milky Way, it has a dense central bulge, sweeping spiral arms, and a large surrounding halo of stars and globular clusters. It is, in many ways, our twin, a sister galaxy with whom we share much in common. And we will share even more in the future. The Andromeda Galaxy is not simply our nearest neighbor, it is heading toward us. Measurements of its motion show that Andromeda is approaching the Milky Way at about 110 kilometers per second. In roughly 4.5 billion years, about the same time it took Earth to form from a nebula, the Andromeda Galaxy and the Milky Way will begin their slow gravitational dance of merger. This sounds dramatic, and it will be over billions of years. The two galaxies will pass through each other, then drift apart, then fall back together, then merge. Stars will be thrown out of their current orbits into new ones. The galaxy shapes will distort dramatically. New waves of star formation will be triggered by the collision of gas clouds. The night sky as seen from any surviving planets will change beyond recognition, eventually becoming a brilliant river of light in all directions as the two galaxies become one. But here is the beautiful, reassuring part. Because the distances between individual stars are so vast, the actual probability that any two specific stars will collide during the merger is almost zero. The two galaxies are mostly empty space, and they will mostly pass through each other like two clouds of fireflies mingling in the dark. The stars will be rearranged, not destroyed. Life, if it exists anywhere in either galaxy, would have no reason to notice anything unusual for millions of years. The merged galaxy, sometimes called Milkomeda by astronomers, which I find both amusing and charming, will probably be an elliptical galaxy, large and featureless compared to the elegant spirals that preceded it. But it will contain all the stars from both galaxies, now gathered into one great community. All the planets, all the possible worlds, all brought together. Other galaxies lie within reach of large telescopes but visible to the naked eye are the Triangulum Galaxy, also called Messier 33, the third largest galaxy in our local group. It sits about 3 million light-years away and is a beautiful face-on spiral. When conditions are perfect and the sky is very dark, it can just barely be glimpsed without optical aid. Its face-on orientation means we can see its spiral structure beautifully in photographs, the arms unwinding gracefully from the central core. Beyond our local group, the universe opens out into a vast cosmic web of galaxy clusters and filaments, structures so large that they contain thousands of galaxies, spread across hundreds of millions of light-years. But tonight we are staying closer to home. Close enough to feel the reassuring presence of our galactic neighbors, the familiar lights in the windows of our cosmic street. The merged galaxy, sometimes called Milkomeda by astronomers, which I find both amusing and charming, will probably be an elliptical galaxy, large and featureless compared to the elegant spirals that preceded it. But it will contain all the stars from both galaxies, now gathered into one great community. All the planets, all the possible worlds, all brought together. Other galaxies lie within reach of large telescopes but visible to the naked eye are the Triangulum Galaxy, also called Messier 33, the third largest galaxy in our local group. It sits about 3 million light-years away and is a beautiful face-on spiral. When conditions are perfect and the sky is very dark, it can just barely be glimpsed without optical aid. Its face-on orientation means we can see its spiral structure beautifully in photographs, the arms unwinding gracefully from the central core. Beyond our local group, the universe opens out into a vast cosmic web of galaxy clusters and filaments, structures so large that they contain thousands of galaxies, spread across hundreds of millions of light-years. But tonight we are staying closer to home. Close enough to feel the reassuring presence of our galactic neighbors, the familiar lights in the windows of our cosmic street. Meteor showers and shooting stars. Let's return now from those vast distances and come back to something more immediate, something you can witness directly on any clear night, the gentle drifting magic of shooting stars. Shooting stars, or meteors to use the technical term, are one of the oldest and most universally beloved spectacles in the night sky. They require nothing to appreciate. No telescope, no binoculars, no special knowledge, no particular location. Just a clear night, a bit of darkness, and the patience to look up and wait. And the reward is that sudden, unexpected flash of light. A streak across the sky, lasting a second or two, sometimes leaving a faint glowing train that lingers for a moment before fading. It is brief and beautiful and somehow always surprising, even after you've seen hundreds. What you're seeing when you watch a meteor is not a star falling. It is a tiny piece of debris, often no larger than a grain of sand, rarely larger than a pea, burning up as it enters Earth's atmosphere. These particles travel at extraordinary speeds, typically between 11 and 72 kilometers per second, and when they hit the thin upper atmosphere, the friction with air molecules heats them to thousands of degrees almost instantly. They ablate, vaporize and ionize, leaving a brief glowing trail of hot gas and plasma. This entire process happens at altitudes of roughly 80 to 120 kilometers, in the tenuous upper atmosphere, and it is over in a second or two. The vast majority of meteors are so tiny that they do not reach the ground. They are completely consumed in the upper atmosphere, transformed from solid matter into light and then into dispersed gas, joining the long journey of matter through the universe. Only larger objects, those the size of a fist or larger, survive the passage through the atmosphere to reach the ground as meteorites. And even larger objects, rare but real, can cause dramatic airbursts like the Chelyabinsk meteor of 2013, which exploded over Russia with the energy of a small nuclear weapon, shattering windows for miles around. But the delicate shooting stars we watch on quiet nights are nothing like that. They are gentle. They are brief. They are beautiful. Meteor showers occur when Earth passes through a stream of debris left behind by a comet. Comets are icy bodies that travel on long elliptical orbits around the Sun. When a comet passes close to the Sun, it warms up and material, ice, dust, rock, is blown off its surface by solar radiation and the solar wind. This material spreads out along the comet's orbital path, leaving a trail of debris that can persist for thousands or millions of years. When Earth's orbit intersects this debris trail, we pass through it every year at the same time, and for a few nights, we encounter far more meteors than usual as the debris particles rain into our atmosphere. The Perseids, which peak in mid-August, are perhaps the most beloved meteor shower in the northern hemisphere. They are produced by debris from comet Swift-Tuttle, a large comet that last passed close to the Sun in 1992. Every August, Earth passes through the debris trail it has left over many orbits, and on the peak night, you might see 80 to 100 meteors per hour under ideal dark sky conditions. The Perseids are well loved partly because they occur in the warm summer nights, when lying outside to watch the sky is genuinely comfortable and pleasant. The meteors of any particular shower appear to radiate from a single point in the sky, called the radiant. This is a perspective effect. It's the same phenomenon that makes parallel railway tracks appear to converge at a point in the distance. All the meteor debris is traveling in the same direction, the direction of Earth's orbital motion through the debris stream, so the meteors all appear to come from the same direction. The Perseids appear to radiate from the constellation Perseus, hence the name. The Leonids appear to come from Leo, the Geminids from Gemini, and so on. The Geminids in December are actually the most intense regular meteor shower, potentially producing over 100 meteors per hour at peak. What makes the Geminids unusual is their source. Unlike most meteor showers which are produced by comet debris, the Geminids come from an asteroid called 3200 Phaeton. An asteroid, a rocky body, shedding debris like a comet, creating one of the most spectacular meteor showers of the year. Phaeton may be a former comet that exhausted its ice long ago, or it may represent a new type of object that we don't fully understand yet. The Leonids, peaking in mid-November, are famous for their occasional meteor storms, brief periods, occurring roughly every 33 years when Earth passes through a particularly dense part of the Leonid debris stream, when the rate can climb to thousands of meteors per hour. In 1833, a Leonid storm produced what witnesses described as a rain of fire, with shooting stars so dense that they seemed to fill the entire sky. In 1966, another Leonid storm produced estimated rates of 40 to 150 meteors per second, not per hour, per second. Observers reported that the sky seemed to be falling. Most meteor showers are gentler. On a typical non-shower night, you can still see 5 or 10 random meteors per hour, called sporadic meteors, if you have a dark sky and you're patient. These are debris particles from various sources, hitting Earth's atmosphere at random times and from random directions. They require nothing but a clear night and a willingness to look up and wait. Making a wish on a shooting star is perhaps the sweetest intersection of human longing and astronomical reality. Why do we make wishes? There is something about the shooting star's brevity, its unexpected beauty, its appearance and disappearance in a single breath, that creates a tiny window of feeling, a moment of hope or wonder that the human heart instinctively wants to fill with something hopeful. Every culture that has seen shooting stars has developed traditions around them. In many European traditions, a shooting star means a soul is ascending to heaven. In other traditions, it is a sign of good luck, a moment when the universe is paying attention. Whatever the mythology, the underlying human impulse is the same. When something beautiful and unexpected appears in the sky, we want to respond with hope. So tonight, if you see a shooting star, if your mind is still awake enough in the quiet of this night, make a wish. The universe, after all, has been at this for 13.8 billion years. It has seen many wishes. It may have a few more good things to offer. The northern lights, the sky as canvas. Let's talk about one of the most beautiful things the sky has to offer. The aurora borealis, the northern lights, that extraordinary light show that has captivated humans in high latitudes for all of recorded history. The aurora is, at its heart, the result of a gentle conversation between our sun and our atmosphere. The sun constantly emits a stream of charged particles, electrons and protons, called the solar wind. These particles stream outward from the sun in all directions, filling the space of the solar system with a constant, gentle flow. When they reach Earth, most of them are deflected by Earth's magnetic field, the invisible shield that surrounds our planet and protects us from being stripped of our atmosphere, the way Mars was long ago. But Earth's magnetic field has two weak points, the magnetic poles. Near the poles, the field lines converge and dip toward the planet, and some of the charged particles from the solar wind are channeled along these field lines down into the atmosphere. When these energetic particles collide with atoms and molecules of oxygen and nitrogen in the upper atmosphere, at altitudes of about 100 to 300 kilometers, they excite those atoms, boosting electrons to higher energy states. When the electrons fall back down to their normal states, they release photons of light. This is the aurora. The color of an aurora depends on which atmospheric gas is emitting the light and at what altitude. Oxygen at high altitudes above 200 kilometers glows a rare crimson red. Oxygen at lower altitudes around 100 to 150 kilometers produces the most common aurora color, a vivid, luminous green. Nitrogen produces a blue or purple color. The interplay of all of these, green curtains with pink and red fringes, blue and purple ribbons at the lower edges, creates the aurora's characteristic color palette. The aurora appears in different forms, all of them beautiful. Sometimes it is a simple arc, a low, steady glow on the northern horizon. Sometimes it is bands, moving, rippling curtains of light that shift and fold like silk scarves caught in a breeze. Sometimes it is rays, streaming upward from a central point like the spokes of a great celestial wheel. And at its most active, it can fill the entire sky in a great corona, a swirling, pulsating display that seems to come from directly overhead, making the observer feel like they are standing inside the light itself. The intensity of the aurora is tied to solar activity. During periods of increased solar activity, solar flares, coronal mass ejections, sunspot groups, great bursts of charged particles are fired from the sun's surface and travel through space to reach Earth in 1 to 3 days. When these intense bursts interact with Earth's magnetic field, the auroral displays can be spectacular, extending far further toward the equator than usual. Strong aurora events have been seen as far south as the Caribbean and as far north as the equator in extreme cases, rare but documented events. The best places to see the aurora regularly are in a band around the magnetic poles called the auroral oval, roughly corresponding to latitudes of 65 to 72 degrees in the northern hemisphere. This includes Alaska, northern Canada, Iceland, Norway, Sweden, Finland, and northern Russia. In these places, on clear nights during periods of even moderate solar activity, the aurora is a frequent companion, not a once-in-a-lifetime spectacle but a regular evening visitor, as ordinary and as extraordinary as a sunset. The southern hemisphere has its own aurora, the aurora australis, the southern lights, though it is less well known simply because the most southerly latitudes where it regularly appears, southern Argentina, the Falkland Islands, the southern tips of New Zealand and Australia, are sparsely populated. From Antarctica, the aurora australis can be as spectacular as anything seen in the Arctic. Cultures of the high north have been watching and interpreting the aurora for thousands of years. The Norse saw the aurora as reflections from the shields of the Valkyries, riding across the sky. The Sami people of northern Scandinavia and Finland treated the aurora with reverence and caution. It was sometimes seen as the spirits of the dead. In parts of Greenland and the Canadian Arctic, the aurora was thought to be the spirits of the dead playing games, and there were traditions of whistling or waving at the lights to attract them. Some traditions warned against making too much noise under the aurora. In others, the lights were benevolent ancestors watching over the living. All of these traditions share something: the recognition that the aurora is alive in some sense, that it moves and breathes and responds, that it fills the sky with something beyond ordinary light. Scientifically, we know that it is charged particles colliding with gas molecules in the upper atmosphere. But watching it ripple across the sky, green and violet and deep red, shifting and folding in ways that seem almost intentional, it is hard to argue that it feels like less than something extraordinary. I like to think about the aurora as the sky's most direct communication with the sun. Every other form of sunlight comes to us passively. We orbit, we receive. But the aurora is the sun reaching out and touching our magnetic field, and in the collision producing beauty. It is an interaction, a response, a light show created by the meeting of two systems. In that sense, it is different from every other thing in the night sky. It is not a distant point of ancient light. It is happening right now in the atmosphere above us, the sun and the earth creating something together. Ancient stargazers, humanity's long relationship with the sky. We have been traveling through the sky tonight, visiting stars and nebulae and galaxies. But I want to take a moment now to travel back in time, to think about the long, extraordinary relationship between human beings and the night sky. Because that relationship is, in its own way, as vast and beautiful as the cosmos itself. Humans have been watching the sky for as long as we have existed. Long before writing, long before cities, long before agriculture, before any of the things we usually associate with civilization, our ancestors looked up at night and saw something that moved them. Something that required attention, interpretation, response. The oldest confirmed astronomical records are cave paintings in Europe dating back 17,000 to 40,000 years, which some researchers believe depict star patterns including what may be the Pleiades and what may be Orion. These are not certainties. The interpretation of very old images is always uncertain, but the possibility is genuinely exciting. It suggests that the same star patterns that capture our attention today may have been traced and memorized by people who had never seen a city, who made their tools from stone, who sheltered in caves on cold nights not entirely different from this one. They looked up. They saw what we see. And they thought it was important enough to paint on a wall. The astronomical tradition of Aboriginal Australians is remarkable, and I want to spend some time with it because it represents something genuinely unique in human history. Aboriginal peoples have maintained unbroken oral traditions about the night sky for at least 65,000 years, making it not just the oldest astronomical tradition in the world, but the oldest continuously maintained intellectual tradition of any kind. 65,000 years. To put this in perspective, the oldest writing in the world is about 5,000 years old. The oldest astronomical texts from Mesopotamia are about 4,000 years old. Aboriginal astronomical knowledge is more than 10 times older than any written record. This knowledge has been preserved not in writing but in song, story, dance, and ceremony, living oral traditions passed from elder to student across hundreds of generations. The knowledge includes detailed understanding of the regular cycles of stars and their relationships to seasons, plants, animals, and human activities. Aboriginal peoples used the rising and setting of particular stars to mark the right time to move to certain locations, to expect certain foods to be available, to undertake certain ceremonies. The night sky was not separate from practical life. It was a calendar, a map, a guide. Aboriginal astronomy also recognized what Western astronomy discovered only recently: the dark constellations. Most of the world's astronomical traditions focus on the bright stars and the patterns they make. But Aboriginal peoples of Australia also traced patterns in the dark spaces of the Milky Way, the bands of dust that block distant starlight and create irregular dark patches in the galaxy's glow. The emu in the sky, a famous dark constellation, uses these dark patches to trace the silhouette of an emu, and the emu rises at different times of year in correspondence with the availability of emu eggs on the ground. The sky and the land connected by the shape of darkness. It is a beautifully different way of reading the night. The ancient Egyptians had a profound connection to specific stars that shaped their civilization. Their calendar year began with the first heliacal rising of Sirius, the morning when Sirius first becomes visible above the eastern horizon just before dawn after being hidden by the sun for several months. This event reliably preceded the flooding of the Nile by a few weeks, and since the Nile flood was the foundation of Egyptian agriculture, the return of Sirius was the most important astronomical event of the Egyptian year. They personified it as the goddess Sopdet, depicted as a woman with a five-pointed star on her head. Entire temples were oriented to align with Sirius's rising. The Great Pyramid at Giza is also aligned with the cardinal directions with extraordinary precision. Its sides align to true north, south, east, and west within fractions of a degree. The original entrance shaft was aligned to point toward the north celestial pole, not at Polaris, which wasn't the pole star at the time of the pyramid's construction, but at Thuban, the star that occupied the pole position around 2550 BCE when the pyramid was built. Whether this alignment was intentional or symbolic or both is debated, but the precision of the construction, achieved without modern instruments, is humbling. Stonehenge in southern England represents another deep engagement between a prehistoric culture and the sky. The monument as we see it today was built and modified over many centuries, from roughly 3000 BCE to 1500 BCE. Its most famous astronomical alignment is with the midsummer sunrise. On the summer solstice, the rising sun shines directly along the main axis of the monument and illuminates the central altar stone. This alignment is so precise that it could not be accidental. The builders of Stonehenge, over 3,000 years before the birth of Christ, understood the geometry of the sun's movements and encoded it in stone. They built a monument that still works, 3,000 years later, every single year on the same morning. The Mesopotamians, the civilizations of ancient Sumer, Akkad, and Babylon in what is now Iraq, were systematic astronomers as well as mythmakers. They developed the 12 constellation zodiac we still use, the naming of the planets after gods, and detailed records of astronomical events going back to at least 1800 BCE. They understood the periodicity of eclipses well enough to predict them. They tracked Venus with extraordinary care. Some of the oldest astronomical tablets we have record the rising and setting times of Venus with remarkable accuracy. Their astronomical knowledge eventually influenced Greek astronomy, which shaped the Islamic astronomical tradition of the medieval period, which in turn gave us many of the star names we still use today: Aldebaran, Altair, Betelgeuse, Deneb, Fomalhaut, almost all from Arabic, preserving the careful observations of Islamic astronomers who built on Babylonian and Greek foundations. The Maya civilization of Mesoamerica developed one of the most sophisticated astronomical and calendrical systems in the ancient world. The Maya tracked the Venus cycle with extraordinary precision, accurately recording its 584-day synodic period, the time it takes for Venus to return to the same position relative to the Sun as seen from Earth. Their Dresden Codex, one of only 4 surviving Maya books, contains a Venus almanac with predicted dates of Venus's movements accurate to within a few minutes over a period of centuries. The Maya used astronomical alignments extensively in their architecture, and their long count calendar counted time in cycles of 144,000 days, about 394 years, showing a cosmological perspective on time that makes human history feel pleasantly small. Polynesian navigators deserve their own moment of appreciation, because what they achieved is simply extraordinary. The peoples of the Pacific, Hawaiians, Maori, Tahitians, Tongans, and others, sailed tens of thousands of miles of open ocean between island groups scattered across the world's largest ocean, using nothing but the stars, the ocean currents, the wind patterns, wave refraction, and the behavior of birds and marine life. They memorized hundreds of star paths, the courses across the sky traced by specific stars from specific latitudes, and used this knowledge to navigate with precision that allowed them to reliably find islands that were tiny specks in a vast ocean, sometimes after weeks at sea. The settlement of the Pacific, from New Guinea to Hawaii to Easter Island to New Zealand, is one of the greatest navigational achievements in human history. And it was done by people who read the sky with their naked eyes and their deeply trained memories. What I love about all of these traditions, Egyptian, Aboriginal, Mesopotamian, Stonehenge, Maya, Polynesian, and the many others we don't have time to visit tonight, is that they all reflect the same fundamental impulse: humans looking up at the sky and being moved to understand it. Not just to appreciate it, but to map it, to memorize it, to find its rhythms and use them. The night sky has been humanity's shared resource for all of history, our common ceiling, our shared calendar, our universal source of wonder. Long before any other kind of science existed, there was astronomy. Long before any other art was preserved, the patterns of the sky were encoded in stories and songs. The stars were the first great subject of human thought. We are the heirs of all of that. Every time you look up at the night sky tonight, you are participating in a practice that goes back to the earliest humans. You are doing what our ancestors did on nights cold and dark like this one, thousands and tens of thousands of years ago. The same sky, the same stars, the same wondering. Exoplanets, other worlds around other suns. There is a question that is perhaps the oldest in human astronomy, a question that has been asked in different forms by philosophers and scientists and stargazers across all of recorded history. Are we alone? Are there other worlds out there? Other suns with their own planets, their own blue oceans, their own sunsets, possibly their own life? For most of human history, this question couldn't be answered. We could speculate, and ancient Greeks, medieval philosophers, and early scientists did speculate extensively and passionately, but we had no way to actually look. The stars were simply too far away and planets orbiting them too small and too faint to detect. As recently as 1990, we had no confirmed evidence of any planet orbiting any star other than our Sun. And then, in the 1990s and 2000s, things changed remarkably quickly. New detection methods were developed. The radial velocity method, which detects the tiny wobble a planet imparts on its star as they orbit their common center of mass, and the transit method, which detects the tiny dimming of a star's light when a planet passes in front of it. And with these methods, exoplanets, planets orbiting other stars, began to be found. First one, then a few, then dozens, then hundreds. The floodgates opened in 2009 when NASA launched the Kepler Space Telescope, a dedicated planet-hunting mission that stared at a single patch of sky containing about 150,000 stars and watched for planetary transits continuously for 4 years. The results were transformative. Kepler found thousands of planet candidates, most of which have now been confirmed as genuine planets. The data from Kepler didn't just find planets. It allowed astronomers to estimate how common planets are throughout the galaxy. The answer was staggering. Planets are not rare or exceptional. They are everywhere. The average star in the Milky Way probably has at least one planet. Some have many. As of today, astronomers have confirmed more than 5,000 exoplanets, with thousands more candidates awaiting confirmation. And the diversity among them is extraordinary. There are hot Jupiters, enormous gas giants that orbit their stars in just a few days, closer than Mercury is to our Sun, heated to thousands of degrees on their permanent day side and with permanent night on the other. There are super-Earths, rocky planets larger than Earth but smaller than Neptune with no analog in our own solar system. There are ocean worlds, planets where liquid water may cover the entire surface to depths of hundreds of kilometers. There are lava planets so close to their stars that their surfaces are covered in molten rock. There are rogue planets, worlds ejected from their star systems and drifting through interstellar space without a sun, warmed only by their own internal heat. And then there are the most quietly exciting ones, the planets in the habitable zones. The habitable zone around a star is the range of orbital distances at which a planet of the right size and composition could maintain liquid water on its surface. It is sometimes called the Goldilocks zone, not too hot, not too cold, but just right. Our own Earth orbits comfortably within the Sun's habitable zone. And Kepler's data suggest that habitable zone planets are common. Estimates suggest that about 20 to 40% of Sun-like stars may have an Earth-sized planet in their habitable zone. The TRAPPIST-1 system is the most exciting nearby example. At just 39 light-years away, practically next door by stellar standards, a small cool red dwarf star called TRAPPIST-1 is orbited by 7 confirmed rocky planets, all roughly Earth-sized. 3 of them, TRAPPIST-1e, F, and G, orbit within the habitable zone. 7 planets around one star, 3 of them potentially hospitable to life. When this system was announced in 2017, it caused genuine excitement in the scientific community and the general public alike. We don't know if any of these planets has an atmosphere. We don't know if they have water. We don't know if anything lives there. But the fact that they exist, 7 worlds around our neighbor, is itself wonderful. When I think about exoplanets, I think about sunsets. Every star with a planet has sunsets. Every planet with a sun, a star it orbits, sees that star set below its horizon as the planet rotates. And each sunset is different. Different colors depending on the star's color and the planet's atmosphere. Different timing depending on the planet's rotation rate, different sky depending on the number of moons, the thickness of the atmosphere, the presence of clouds. There are, right now, billions of sunsets happening on other worlds around other stars. And some of them may be watched. Some of them may be wondered at. Some of them may inspire in whatever lives there the same feeling that Earth's sunsets inspire in us. That sense of beauty, of transition, of the day completing itself in a final generous gift of color. We don't know yet if we are alone. The honest answer is that we don't know. But we know that worlds are everywhere. We know that the ingredients for life, the carbon, oxygen, nitrogen, water, are common throughout the universe. We know that stars like our sun are common. We know that habitable zone planets are common. And we know that wherever life has found a foothold on Earth, in boiling acid vents on the ocean floor, in the ice of Antarctica, in the baked salt flats of the driest deserts, it has persisted and adapted and found a way. The universe seems to like life. Or at the very least, the universe has arranged itself in a way that makes life possible in many places and perhaps likely in many more. That thought, as you drift toward sleep, seems worth holding close. The deep universe, galaxies beyond counting. Let's travel one more time to the deepest distance we're going to visit tonight. Let's go to the deep universe, to the galaxies that lie beyond our local group, stretching out to the horizon of the observable cosmos. In 1995, the Hubble Space Telescope was pointed at a tiny patch of sky, a region about the size of a grain of sand held at arm's length, that appeared completely empty to all previous observations. No nearby stars. No known objects. Just a tiny sliver of darkness. And for 10 consecutive days, Hubble gathered light from that darkness, collecting photons one by one, building up an image of what lay in that apparently empty spot. The result was one of the most profound images in the history of science, the Hubble Deep Field. When the image was processed and revealed, it showed not emptiness, not darkness, but galaxies. Thousands of galaxies in every shape and color and orientation, going back to the earliest epochs of the universe. Spiral galaxies, elliptical galaxies, irregular galaxies, interacting galaxies, distant points of light that are themselves whole galaxies. All in a patch of sky the size of a grain of sand. Later images, the Hubble Ultra Deep Field, released in 2004, and the Hubble Extreme Deep Field, released in 2012, went even deeper, gathering light for even longer exposures and revealed even more galaxies. The Extreme Deep Field contains about 5,500 galaxies in an area of sky so small that it would take 13 million such images to cover the entire sky. Extrapolating from that, astronomers estimate that the observable universe contains somewhere in the range of 2 trillion galaxies. 2 trillion galaxies. Each one containing hundreds of billions of stars on average. The numbers are so large as to be almost meaningless, but that's okay. You don't have to understand them. You just have to rest in the fact of them. The universe is not intimate. It is not human-scaled. It is vast beyond anything our minds were built to comprehend. And yet here we are, inside it, looking out, building telescopes and doing mathematics and piecing together its story. The most distant galaxies we can see are moving away from us at nearly the speed of light, carried by the expansion of space itself. The light from the most distant objects in the observable universe left those objects over 13 billion years ago, when the universe was still young. We see them not as they are now but as they were, infant galaxies, irregular and chaotic, just beginning the process of organizing themselves into the orderly spirals and ellipticals we see in the nearby universe. The James Webb Space Telescope, launched in December 2021 and entering science operations in 2022, has been our deepest eye into that ancient past. JWST can see infrared light, light stretched by the expansion of the universe from its original wavelengths into the infrared, and it has detected galaxies from when the universe was only a few 100 million years old. These ancient galaxies are surprisingly large and well organized for their age, which has challenged some of our models of how galaxies form and evolve. The universe continues to surprise us. It does not behave exactly as our theories predict, and every surprise is an invitation to understand it more deeply. The cosmic microwave background radiation, the faint glow left over from when the universe was about 380,000 years old and first became transparent to light, fills all of space with a whisper of warmth. Discovered accidentally in 1965 by astronomers Arno Penzias and Robert Wilson, who noticed a persistent background noise in their radio telescope that they couldn't explain. They initially suspected it might be pigeon droppings. The CMB is the oldest light in the universe. It predates all stars, all galaxies, all planets. It is the afterglow of creation itself, still detectable today, filling the entire universe with the memory of a hot, dense, luminous past. When I think about the scale of all of this, the 200 billion stars in our galaxy, the 2 trillion galaxies in the observable universe, the 13.8 billion years of cosmic history, the cosmic microwave background still glowing from the universe's earliest moments, I don't feel small in a diminishing way. I feel small in a liberating way. I feel the way you feel when you stand at the edge of the ocean and let the scale of it wash over you. It is bigger than your problems. It is bigger than your worries. It is bigger than anything that feels urgently important at 3 in the morning. And yet you are in it. You are part of it. You are a temporary arrangement of atoms that emerged from the same initial conditions that produced all of that vastness. You are connected to every star in the sky, not metaphorically but materially, the same basic stuff, the same physics, the same story. You are the universe, grown complex enough to look back at itself and be moved by what it sees. That is not a small thing. That is an extraordinary thing. Section 18. the winter sky, a season's gift. As we begin to slow down our journey through the sky, as we start to let the distant stars and galaxies recede and bring our attention back to the immediate, to the personal, to the quiet night around you right now, let's spend some time with the seasonal sky. Because the constellations are not static. They change with the seasons, a slow procession of figures rising and setting as Earth travels its yearly orbit around the Sun. The winter sky for those in the northern hemisphere is arguably the most spectacular of the year. It is as if the sky decides that the long, cold nights deserve compensation, and offers up its most brilliant stars in exchange for the darkness and cold. Orion leads the procession, rising in the east in the early evening and arching high overhead by midnight. Below him and slightly to his left runs Lepus the Hare, a small gentle constellation that Orion is said to be chasing. The summer sky, warmth in the dark. The summer sky, for northern observers, brings a completely different character. Orion has set, gone to the other side of the Earth. In its place, the great Milky Way spans the sky from north to south in all its glory, and the summer triangle, Vega, Deneb, Altair, blazes overhead. On warm summer nights, when lying outside is comfortable and the air is soft, the Milky Way is at its best. The band of the galaxy stretches from the northeast, where Perseus and Cassiopeia mark the edge of it, southward through Cygnus and Aquila, brightening and broadening as it reaches toward Sagittarius in the south, where the galactic center lies. On the darkest nights, in places far from light pollution, the Milky Way casts a visible shadow. Sagittarius the Archer is one of the richest regions of sky for deep sky objects. Nebulae and clusters that crowd together in the direction of the galactic center. The Lagoon Nebula, the Trifid Nebula, the Omega Nebula, all glow together in a relatively small patch of sky in Sagittarius, a concentration of stellar nurseries unprecedented in any other direction. Even with the naked eye, this region of the Milky Way appears distinctly brighter, more complex, more textured than any other, the dense core of the galaxy shining through veils of gas and dust. Scorpius the Scorpion dominates the southern summer sky, its distinctive hook of a tail curving below the horizon for observers in the northern latitudes but spectacular when seen from tropical and southern regions. Antares, the Scorpion's heart, is a red supergiant comparable to Betelgeuse in size and evolutionary state, another massive, aging star destined for a spectacular end. Its name literally means rival of Mars in Greek, for its reddish color resembles the planet Mars when that planet passes nearby. Near Scorpius and Sagittarius, the sky is dense with globular clusters visible even without a telescope on dark nights. M4, M22, M7, M6. These clusters appear as fuzzy stars to the naked eye but resolve into stunning balls of light in binoculars. The whole southern region of the summer Milky Way is a treasury of deep sky wonders, available to anyone willing to find a dark spot and look. Hercules, high in the summer sky, is one of the largest constellations, a sprawling pattern that represents the great hero of myth, usually depicted upside down and kneeling, in a pose so undignified that ancient Greeks sometimes called it simply the kneeling man. Within Hercules sits Messier 13, the great globular cluster we visited earlier. On a good night, M13 is just visible to the naked eye as a dim point of light, and through binoculars it takes on its characteristic fuzzy, non-stellar appearance that reveals its true nature. Corona Borealis, the Northern Crown, is one of my favorite constellations for its simplicity and elegance. It is tiny, just 7 stars, but they form an almost perfect semicircle, unmistakable once you know it. In mythology, this is the crown of Ariadne, daughter of the Cretan king Minos, placed in the sky by the god Dionysus when he married her. One of the stars in Corona Borealis, called T Coroni Borealis, is a recurrent nova, It periodically brightens dramatically when it accretes material from a companion star, flaring from invisible to naked eye brightness before fading again. Astronomers have been watching it closely in recent years, anticipating its next outburst. When it flares, the northern crown will briefly become a true crown, with one star blazing brighter than all its companions. A letter to the night. We've traveled far tonight. From our own sun, steady and patient in the center of our solar system. Through the neighborhood of nearby stars, Proxima Centauri, Sirius, Vega, all those familiar lights in our local corner of the Milky Way. Through the great star patterns, Orion and his belt, Cassiopeia in her chair, the summer triangle blazing over warm nights, the Pleiades riding the shoulder of Taurus. Into the heart of the Milky Way, that swirling community of hundreds of billions of stars that is our home galaxy. Out to the Andromeda Galaxy, 2.5 million light-years away, our approaching companion in the dark. Through the meteor showers and the northern lights and the ancient traditions of stargazers across every human culture. All the way out to the deep universe, the 2 trillion galaxies, the 13.8 billion years of cosmic history, the ancient light still filling all of space. And now it's time to come home. The night sky, for all its vastness, is also deeply personal. The stars you see tonight are the stars you have always seen. They were the same stars your parents and grandparents looked up at on their own sleepless nights, on their own nights of wonder, on their own nights when the world felt too large and too uncertain and the sky was the only thing that helped. They were the same stars above every act of love in human history, every moment of grief, every birth, every quiet evening that ended well. The stars don't need anything from you tonight. They are not asking you to be productive or efficient or useful. They are simply there, as they have always been, as they will always be, burning with patient, ancient light, letting that light travel billions of miles through empty space to touch the retinas of your eyes. Think about that. Billions of miles. From the heart of some far-off sun, energy generated in a nuclear reaction at millions of degrees, traveling outward through space at the speed of light, crossing light years or decades or centuries of emptiness, finally arriving here, at this particular place, at this particular moment, to be received by you. You specifically. It ended here. The universe is not indifferent. Or rather, even if it is indifferent in the cold scientific sense, the light still arrives. It still finds its way. It still completes its journey by reaching something that can notice it and be changed by it. That is enough. That is everything. You are a person who looked up at the night sky or who wanted to. Who chose, on this particular night, to spend some time in the company of stars. That impulse, toward wonder, toward the sky, toward the kind of awe that quiets the mind and opens the heart, is one of the most distinctly human things there is. It connects you to every person who has ever been moved by the night sky across all of human history. To the Polynesian navigator lying in his canoe beneath a field of stars. To the Egyptian priest watching for the rising of Sirius. To the Aboriginal elder pointing out the emu in the dark patches of the Milky Way. To the person thousands of years from now, who will look at roughly these same stars on their own quiet night and feel something that we would recognize. This is not the end of anything. The stars will be there tomorrow night and the night after and the night after that. Whenever you need them, whenever the noise of the world becomes too much, whenever you need to feel the particular quiet that only comes from looking at something truly large, you can step outside or look out a window or simply close your eyes and remember this and you will find them. They are always there. Let the sky hold you tonight. Let the thought of all those billions of patient fires carry you into sleep. Let your breathing slow the way a pond goes still when the wind dies down. Let the images of nebulae and star clusters and the soft band of the Milky Way drift through your mind like a slow, easy tide. You don't need to hold on to anything. You don't need to do anything. You can simply rest here in the dark beneath the sky. The stars are watching. The universe is patient. The night is quiet and full of light. Sleep well. Dream of stars. Good night.